Welcome to the New Chemist. We're glad you're listening. Feel free to download this podcast on Google Podcasts, Apple Podcasts, Spotify, and other platforms. Here on the New Chemist, we discuss chemistry, which simply put is the science of change, as well as careers, community, research, and COVID-19. We're happy you're tuning in.
Welcome to the New Chemist Podcast, Season 10. We're glad you're listening. Feel free to download this podcast on TuneIn Radio, Anchor, Odyssey, and Apple Podcasts, and other platforms. On this podcast, we discuss chemistry, which simply put is the science of change. Also, we discuss careers, research, and Nobel Prize laureate speeches in chemistry. We also interview thought leaders, science professors, educators, administrators, and pioneers in their respective fields. Thanks again for listening. Today, we will discuss a portion of the work of Dr. R.B. Woodward and read his entire Nobel Prize Lecture in Chemistry from 1965. So some vast facts about Dr. Woodward. The Nobel Prize in Chemistry was awarded to Woodward in 1965. He was born in April in 1917 in Boston, Massachusetts. Died in July 1979 in Cambridge, Massachusetts. At the time of the award, he was at Harvard University. The prize was awarded for his outstanding achievements in the art of organic synthesis. Key takeaways. So I'm going to read these key takeaways before we begin reading the speech, so that you have these key points to note and to understand and also to take record of. So, what is cephalosporin? Cephalosporin C, as discussed in Woodward's speech, is a product of the metabolism of Cephalosporin acremonium, which is a type of fungi. What is penicillin G, otherwise known as benzyl penicillin or benpen, is, according to PubChem, a broad spectrum beta-lactam, naturally occurring penicillin antibiotic with antibacterial activity. Penicillin G binds to and inactivates the penicillin binding proteins, PBPs, located inside the bacterial cell wall. Inactivation of PBPs interferes with the cross-linkage of the peptidoglycan chains necessary for bacterial cell wall strength and rigidity. This interrupts bacterial cell wall synthesis and results in the weakening of the bacterial cell wall and eventually causing cell lysis. What is one reason why the synthesis is important? It helps to advance the field of natural products and drug synthesis. So, we're going to read R.B. Woodward's speech entitled Recent Advances in the Chemistry of Natural Products. It was a Nobel Lecture given on December 11th, 1965. So let's begin. The Nobel Prize in Chemistry for 1965 has been awarded for contributions to the art of chemical synthesis. It gives me much pleasure to record here my gratification with a citation, which properly signalizes an exciting and significant aspect of synthetic activity. But that aspect is one which is more readily, and I dare say more effectively, exemplified and epitomized than it is articulated and summarized. Having here this morning the responsibility of delivering a lecture on a topic related to the work for which the prize was awarded, I have chosen to present an account of an entirely new and hitherto unreported investigation, which I hope will illuminate many facets of the spirit of contemporary work in chemical synthesis. Cephalosporin C, a product of the metabolism of cephalosporin acremonium, was isolated in 1955 by Newton and Abraham in an investigation notable for its perspicacity, as well as its painstaking attention to detail. The investigation of the structure of the metabolite was successfully concluded in 1961 through studies in which both chemical and X-ray crystallographic techniques were employed. The molecular array, thus laid bare, strikes one at once as having affinities with a hitherto well-known class of substances, which has constituted one of the most challenging and recalcitrant synthetic objectives of our generation. I refer, of course, to the penicillins, of which penicillin G, one of the earliest known and one which has been widely used in medicine, may serve as an example. There can be few organic chemists who do not know the fascinating history of the penicillins. How, following up an early observation of Alexander Fleming, Chain and Florey, isolated the first penicillin shortly after the outbreak of the Second World War. How the powerful practical desiderata of those trying times led to the establishment of a mammoth British-American program which had as its objectives the determination of the structure and the synthesis of the penicillins. How the chemical investigations, and especially the X-ray crystallographic studies of Dorothy Hodgkin, conquered the structural problem, and how, despite the best efforts of probably the largest number of chemists ever concentrated upon a single objective, the synthetic problem had not been solved when the program was brought to a close at the end of the war. Many chemists continued to be fascinated by the problem, and some were still willing to gamble their skill against its obstinacy. In 1959, after more than a decade of intensive investigation, John Sheehan succeeded in the development of methods by which penicillins could be prepared by total synthesis. That these methods have not come into practical use does not detract from this major achievement, but only emphasizes that the challenge presented to the synthetic chemists by the penicillins has not been exhausted. A parenthesis is probably desirable at this point in order to allay some concern among those who have not been initiated in these matters. I have used the plural term penicillins because nature provides several closely related substances, differing only in the acyl group attached to the nitrogen atom, which is itself situated to the lactam carbonyl group of the general structure. Furthermore, chemists have found ways of removing these acyl groups from the natural representatives of the class, and attaching entirely new and different groupings to the nitrogen atom thus freed. In this way, many hundreds of artificial penicillins have been prepared. The situation is similar in respect to Cephalosporin C, in that a whole class of cephalosporins has been created by replacement of the omega D alpha amino adipole residue of natural metabolite by numerous other acyl groups. In both classes, the penicillins and the cephalosporins, some of the derived substances possess properties which confer on them special utility in medicine. Thus, Cephalosporin C itself possesses antimicrobial activity of a relatively low order of magnitude, which, however, early attracted special interest because it persisted against organisms which had become resistant to the penicillins. In some of the derived cephalosporins, this especially interesting aspect of the antimicrobial activity is retained, while at the same time the level of activity is much heightened. Further, the activity extends over the range of gram-negative and gram-positive organisms. Consequently, some of these substances, of which cephalothin 4 may serve as an example, have already achieved utility in medicine as broad-spectrum antibiotics of low toxicity effective against penicillin-resistant organisms. In considering the development of a plan for the synthesis of any complicated substance, it is always desirable to look at the problem from an entirely fresh point of view. Nevertheless, in the case at hand, it was pertinent to examine whether the experience gained and the results achieved in synthetic studies on the penicillins might be usefully applicable to the structurally related cephalosporins. We rejected the possibility at the outset for several reasons. I've already alluded to the fact that the known penicillin syntheses hard-won brilliant achievements, though they are lacking in practicality. Further, the problems which had to be overcome in devising methods for penicillin synthesis had been quite difficult enough without adding to them the intricacies which would have been associated with the achievement of stereospecificity in the creation of asymmetric intermediates, and this aspect had been slightly slighted. Finally, a special chemical point was of much importance. The beta-lactam ring common to the penicillins and the cephalosporins is highly susceptible to hydrolytic cleavage. In the case, for example, of penicillin G, the product of this hydrolysis is the penicilloic acid. The synthesis of penicilloic acid and its analogues, at least by non-stereospecific methods, was a relatively simple problem, and by far the largest number of attempts to synthesize penicillins, and the only successful ones, involved the deceptively simple task of removing the elements of water from penicilloic acid analogues with the closure of four-membered beta-lactam ring. In the case of the cephalosporins, the situation is strikingly different. Here, the beta-lactam ring is also easily cleaved, but the proximate product of the hydrolysis, which must have the structure 4, 5, 6, is not a known substance. Its intricate and delicate constitution is such that it does not survive even the mild conditions of its generation from the corresponding lactam. Clearly, then, it would be unwise to essay the synthesis of cephalosporin from such a hitherto unknown and obviously highly fugitive precursor. Often in the course of synthetic work, one or two key ideas set the style, development, and outcome of the investigation, while providing the flexibility essential for any long journey through unknown territory, beset with perils which at best can be only dimly foreseen. In planning our synthesis of cephalosporin, the first of these definitive concepts was of our choice of the L-cysteine as our starting material. This readily available substance possesses a 2-carbon backbone, to which are attached a carboxyl group, an alpha nitrogen atom, and a beta sulfur atom. In short, it presents in ready-made fashion a large portion of the crucial substituted beta-lactam moiety of the cephalosporins. Furthermore, it is optimally active, and the groups arranged about its one asymmetric carbon atom are oriented in an absolute stereochemical sense, precisely as are the similar groups in the objective, that is to say, as soon as the decision to use cysteine had been made, our stereochemical problem was, in a sense, already half solved, since the cephalosporin nucleus contains only one further asymmetric center. On the other hand, advantageous as this choice obviously was in many ways, it was also clear that associated with it was a special problem, which could by no means be viewed lightly. The cysteine molecule is a tightly assembled package of highly reactive groupings: the amino group, the sulfur-hydryl group, the carboxyl group, and the alpha-methine group. Each possess characteristic features of chemical reactivity and represent points at which ready modification of the molecule might be expected. But the only remaining feature of the molecule, the simple saturated beta-methylene group, represents a point at which there is little or no precedent for chemical attack. And yet, in light of our plan, we must in some way introduce a nitrogen atom at that point, preferably in a stereospecific manner. Further, even assuming that a method should be discovered for overcoming the defenses of the molecule at that strong point, it was clear that we should be dealing with intermediates containing two electronegative atoms bound to the same carbon atom, a situation well known for its potentialities in conferring sensitivity and instability upon molecules so constituted. In sum, our initial decision placed us in the exhilarating position of having to make a discovery and of being prepared to deal with substances of an especially precarious constitution. Our first actual operations consisted quite naturally in so modifying the cysteine structure as to depress the reactivity of the amino, sulfur-hydryl, and carboxyl groups. Thus, the amino acid was first converted by reaction with acetone into the thiazolidine, which is in its turn reacted with tert-butyloxycarbonyl chloride in the presence of pyridine to give the corresponding N-tert-butyloxycarbonyl compound. Some special interest attaches to the fact that the acylation reaction undoubtedly takes place to internal delivery of the N-tert-butyloxy group, which first becomes attached at the carboxyl site to give the mixed anhydride. The acylated thiazolidine was next converted into the methyl ester with diazomethane. These three simple changes had sufficed to convert the cysteine molecule into one whose methylene group might now enjoy a far better relative position in respect to reactivity as compared with the same grouping in the original cysteine. But they also served another function. By incorporating the methylene group in a ring, and thereby rendering rotation about the alpha-beta carbon-carbon bond impossible, we had set the stage for bringing about transformations at the methylene group in a stereospecific manner. I shall not detail here the many weapons which were brought into play against that still expectedly recalcitrant methylene grouping. Suffice it to say that the protected ester reacted with excess dimethyl azodicarboxylate at 105 degrees during 45 hours to give the hydrazodiester an almost quantitative yield. It is of special interest that we have been able to assemble evidence which suggests that this novel reaction involves initial attack of the sulfur atom upon the azo grouping, and that the formation of this bond may be concerted with the migration of hydrogen from the methylene group to the second nitrogen atom. Thus, if substances containing free active hydrogen, such as the acid and the benzene sulfonamide, are brought into reaction with dimethyl azodicarbooxylate, attack upon the methane group is now observed, and the products contain an actual sulfur-nitrogen bond. Further, we have been unable to observe an intramolecular version of the reaction, for example, with the corresponding with the compound. A circumstance which we connect with a very unfavorable geometry, in this case, a transition state in which hydrogen moves as sulfur attacks nitrogen. Another special point of interest is that the conditions for the reaction. Simple though they are, must be adhered to rigorously. At lower temperatures, reaction is too slow to be useful, while if the temperature is raised only a small amount. The reaction is much less clean. And among the products is the unmethylated derivative. In any event, the new reaction was propitious in that we had achieved a substitution of the desired site, and in that the newly attached grouping was one which might be expected to exhibit selective reactivity. A very important point is that the reaction is stereospecific. The dihydrazodiester grouping is introduced solely on one side of the ring. Clearly, this result is associated with the presence of the carbomethoxyl grouping, whose bulk deprives the attacking moiety of the opportunity for attachment on the alternative side of the relatively rigid 5-membered ring. Of course, the stereospecificity here exhibited was in a way precisely the wrong kind. Since what we required was the introduction of a nitrogen atom on the same side of the ring as the carbomethoxyl group. But this simply meant that we must now replace the newly introduced group with the inversion of configuration of the beta carbon atom. A task which we might have taken in hand with little apprehension had it not been for the presence of the sulfur atom, whose attachment to the center at which inversion was required might render invertible intermediates non-existent or malefactory. When the hydrazodiester was oxidized in boiling benzene for 2 hours, using somewhat more than 2 moles of lead tetraacetate, the resulting reaction mixture was treated with the excess anhydrous sodium acetate and boiling dry methanol for 24 hours. The transhydroxy ester was produced. The sequence is not as simple as it might at first appear, and we know some of the intermediary stages through which it proceeds. It is reasonable to suppose that the hydrazole compound, like all hydrazine derivatives, is susceptible to removal of 2 electrons by an oxidant. This resulting species must lose a carbomethoxyl group, very readily to be to an available nucleophile. The product is of a type which would be expected to be transformed further by lead tetraacetate into an acetoxy-azo compound. The spectroscopic evidence for the presence of such an intermediate at the conclusion of the lead tetraacetate oxidation is convincing, when compared with the parallel characteristics of a similar compound isolated in the crystalline state and fully characterized. After oxidation of the sulfonamide, the next change is the loss of a second carbomethoxyl group. Again, under nucleophilic attack, followed by loss of elementary nitrogen and the accession of a proton to the beta carbon atom. The final change is a simple base catalyzed methanolysis of the acetoxy group. Special note should be made of the fact that these transformations involve a replacement at an asymmetric center. This replacement is stereoselective in that by far the major product is the trans-acetoxy ester, without the bulk of the adjacent carbomethoxyl group plays its role in forcing the acetoxy group into a more spacious location. Nonetheless, a small amount of cis-acetoxy ester is produced, but for reasons which will be developed shortly, this minor departure from stereospecificity is corrected almost at once. The very existence of the trans-hydroxy ester deserves special comment. It should first be noted that its structure was established with definitive rigor through its preparation by the action of diazomethane upon the corresponding acid. This acid was synthesized by a series of reactions similar to those outlined above, except that the carboxyl group of the thiazolidine was protected by the attachment of the beta-beta-beta trichloroethyl grouping, which was removed reductively after the introduction of the beta-hydroxy group. The structure of the hydroxy acid was established beyond any question by a complete three-dimensional X-ray crystallographic study brilliantly executed by Dr. Gugatas in Cambridge. We have already alluded to the potentiality for instability inherent in the attachment of more than one electronegative atom to the same carbon atom, and it will be useful at this point to illustrate in some detail the factors which might have hurled us from the plateau on which we are now standing. Thus, the hydroxy ester is an obvious candidate for participation in ring chain tautomerism as an open chain isomer, which in its turn, possessing as it does a beta dicarbonyl system, could readily undergo essentially irreversible tautomerization to a stable beta hydroxyacrylic ester. The same substance might alternatively be reached directly through a ready beta elimination of the sulfur atom. Either of these sulfur hydrotonomers might well lose thioacetone to give the corresponding N-monosubstituted urethane. Finally, it would have not been surprising if the newly introduced hydroxyl group, or indeed any of the newly introduced beta-disposed groupings along the way, had been susceptible of ready elimination for the formation of the thiazolidine. The hydroxy ester is, in the event, a stable manipulable compound that it does not too readily succumb to these potentialities for its self-destruction. Was a major new result of our investigation so far. We can in fact say something more about these potentialities at this time. It was mentioned above that at one stage in the replacement of the hydrazo diester grouping by the hydroxyl group, a certain amount of cis-acetoxy ester is produced at an intermediary stage. Yet the sole product of the whole sequence is the trans-hydroxy ester. From our work with the trichloroethyl ester, the cis and trans-acetoxy acids, and have been isolated and two compounds which have been isolated in pure crystalline state, each of these stereoisomeric substances is transformed on hydrolysis into the same trans-hydroxy compound. Thus, it is clear that the hydroxy compounds do participate in ring chain tautomerism. But the reclosure of the open chain aldehyde is so much favored over internalization of the aldehyde group, or loss of thioacetone. These latter changes, which have been fatal to our prospects, do not obtrude. The hydroxy ester was now transformed by treatment in dimethylformamide with excess diisopropylethylamine and methane sulfonyl chloride, followed by concentrated aqueous sodium azide to the cis-azidoester, which was in turn reduced in methanol solution by aluminum. Amalgam at negative 15 degrees during 24 hours to the cis-amino ester. The structure of the latter was again confirmed by a complete X-ray crystallographic study carried out by Dr. Gugatas. It is clear that this sequence of changes involves the intermediacy of the methane sulfonyl derivative, which does, in the event, undergo normal bimolecular nucleophilic displacement with inversion in the classical mold when attacked by an acyl ion. The dread possibility that the intermediary sulfonate might be too readily susceptible of ionization to a cation, which would have led on to the thiazolane or to stereochemically indiscriminate or undesired substitution of the beta-carbon atom, was fortunately not manifest. No doubt, avoidance of this danger is associated with the predictable relatively high energy of the electronic configuration. At this point, we have succeeded in the major objective of introducing a properly oriented nitrogen atom into the beta position of the cysteine moiety. In short, the entire stereochemical problem presented by the cephalosporins had now been solved. It is appropriate here to introduce the second of the key ideas upon which our general plan was based. It was that we should attempt the preparation of beta-lactam, having it in mind that the substance, if procurable, will contain the basic structural elements common to the cephalosporins and the penicillins, and that it might serve as a source of a wide variety of known and new substances through the fusion of new rings at the presumably reactive nitrogen and sulfur atoms. The cis-amino ester now in hand differed from the desired lactam only by the elements of a molecule of methanol. The attachment of the amino and carbomethoxyl groups in 38 to a relatively rigid ring system might be expected to favor formation of a new ring. It was an interesting feature of the X-ray crystallographic study that the distance between the amino nitrogen atom and the carbonyl carbon atom was unusually low. In all these circumstances, we felt that the stage had been well set, and we were gratified to find that when the cis-amino ester was treated with triisobutyl aluminum and toluene, it was in fact converted into the desired beta-lactam. Again, the very existence of this substance, containing as it does potentialities for annihilation, parallel to those discussed above in some detail for the hydroxy ester, further compounded by the desirable strain within the beta-lactam ring. Represents a major result of our investigation. In view of the importance of the intermediate, its structure was established in detail and with complete rigor through yet a further three-dimensional X-ray crystallographic investigation by Dr. Gugatas. Our success with the remarkable series of substances I have described, must tend to obscure the venturous spirit with which their investigation could not have had been taken in hand, lest it still be felt that our concern with the liability and versatility of our intermediates had been chimerical. It may be mentioned that the phosphinamine prepared from the acidoester and the tri-N-butylphosphine gave on hydrolysis, even under the mildest conditions, in addition to the cis-amino ester, appreciable quantities of the trans-amino ester and the stable non-cyclizable open-chain isomer. Clearly, the formation of these substances involves subtly determined tautomeric changes closely parallel to those discussed in detail in respect to the hydroxy ester. We were now ready to reduce the practice our presumption that the beta-lactam would be a versatile intermediate, capable of further development through fusion of further atomic groupings of the reactive nitrogen and sulfur atoms. In order to procure a suitable component for combination with the beta-lactam, D-tartaric acid was converted into its di-beta-beta-beta trichloroethyl ester, and the latter was oxidized using sodium metaperioidate in aqueous methanol. 2-beta-beta-beta trichloroethyl glyoxylate, isolated as a corresponding hydrate. The substance was condensed in aqueous solution with a sodium salt of malone dialdehyde to give an aldol of the structure. The aldol condensation product, in its turn, lost a molecule of water when it was heated in normal octane. The novel highly reactive dialdehyde was produced. This powerful electrophile was chosen in the hope that it might combine directly with a substance containing active hydrogen in a concerted cycloaddition process requiring no catalysis. The desire to avoid catalysis in reactions. In reactions involving the beta-lactam was of course a consequence of our apprehension that such substances might well mobilize one or more of the capacities for self-destruction inherent in the intricate construction of our key intermediate. In the event when the beta-lactam was heated with the dialdehyde in normal octane at 80 degrees during 16 hours, combination took place in the desired fashion and the adduct was produced. The latter, in its turn, when allowed to stand in trifluoroacetic acid at room temperature during 2.5 hours, was transformed to the aminoaldehyde. The general nature of the processes involved in this latter change is clear. In particular, the crucial closure of the new six-membered ring is a consequence of the attack of the strongly electrophilic carbon atom of a protonated carbonyl group upon the nucleophilic sulfur atom. This course of the ancillary changes need not be specified in detail. A number of more or less equivalent schemes may be considered, among which those portrayed in 53 and 54 should be included. A special point is that the amino group which is ultimately freed very probably appears at some time during reaction as a corresponding shift base. We have found that shift bases are readily cleaved in trifluoroacidic solution. In any event, from the practical point of view, it was most gratifying that the protecting groups, that is the N-terminal tert butyl oxycarbonyl group and the bridging isopropylidene group, which had so well served their several purposes, were now no longer wanted to remove concomitantly with the crucial formation of the newly six-membered ring. Mention should be made at this point of a special stereochemical detail. The adduct contains one asymmetric carbon atom, in addition to those present in the beta-lactam. The combination reaction gives both of the a priori possible products, which have been separated and carefully characterized. Although the matter is under active study, we cannot as yet make rigorous stereochemical assignments for the two isomers. In any event, the point is not an important one from the practical point of view, and as we shall see shortly, asymmetry at the center under discussion is expunged in subsequent operations. The aminoaldehyde was next isolated in benzene solution with thiophene to acetyl chloride in the presence of pyridine, and the resulting amide was reduced using diboron in tetrahydrothioane solution to the alcohol. The latter was acetylated in normal way with acetic anhydride and pyridine to give the isocephalothane beta-beta-beta trichloroethyl ester. In turn, this beta-gamma unsaturated ester was smoothly equilibrated with the corresponding alpha-beta unsaturated isomer, cephalothane beta-beta-beta trichloroethyl ester, when it was allowed to stand in anhydrous pyridine solution at room temperature for 3 days. Also, the beta-gamma unsaturated isomer is favored in this equilibrium. The two isomers were found to be readily separable by chromatography and silica gel. The conjugated ester was now reduced by zinc dust in 90 degrees aqueous acetic acid at room temperature, and cephalothane was obtained. The properties of the synthetic substances were identical in all respects. Of material prepared from natural cephalosporin C. The final step in our synthesis of cephalothane, namely the reductive removal of the beta-beta-beta dichloro grouping, is worthy of special comment. In planning our work, it has been clear that the group destined to become the free carboxyl group function of the final cephalosporin must appear in some protected form during the intermediary stages. Further, protection must be such that it could be removed without doing violence to the highly sensitive beta-lactam ring, which is especially prone to hydrolytic attack. Some years before in Cambridge, Mr. Kohler, faced with a not dissimilar problem at my instigation, investigated in a preliminary way the action of the reductants upon beta-beta-beta trichloroethyl derivatives, with very encouraging results. The idea had been that an electron source could bring about considered elimination process, which might be highly favored on statistical grounds, as well through the capacity of the chlorine atoms not directly involved in the elimination process to facilitate electron accession in the transition state. As we have seen, and as further examples in the sequel will show, the grouping served the desired function admirably in our work in the cephalosporin field. And we suggest that it may well find some general utility. Indeed, Dr. Fritz Exning, encouraged by his knowledge of our early studies, has very recently shown how it can be put to very good effect in work with the nucleotides. We turn now to the completion of the synthesis of cephalosporin C itself. The aminoaldehyde was in this case condensed in tetrahydrofuran solution, the end beta-beta-beta trichloroethylcarbonyl D-alpha-aminoadipoic acid in the presence of dicyclohexyl carbodiamide. The resulting crude mixture was then esterified directly with the beta-beta-beta trichloroethanol in methylene chloride in the presence of dicyclohexyl carbodiamide and pyridine. The sequence of reactions gave two main products, which readily separated by chromatography and silica gel using benzene ethyl acetate as diluent. molar of the products was 63, since it was converted by reduction in tetrahydrofuran with diborane, followed by acetylation with acetic anhydride, pyridine to give the beta-gamma unsaturated ester. As in Cephalosporin series, this unconjugated ester was smoothly equilibrated with the conjugated isomer when it was allowed to stand in pyridine. At room temperature for 3 days, again the two isomeric esters were readily separated. The conjugate isomer was reduced by zinc dust, 90% aqueous acetic acid at 0 degrees during 2.5 hours to synthetic cephalosporin. The identity of the synthetic material was in this case established through examination of its paper chromatographic behavior in several systems, as well as through observation of its antibacterial activity against Neisseria catarrhalis, alkylogenes faecalis, Staphylococcus aureus, and Bacillus subtilis. Further, synthetic crystalline barium salt with identical in optical and spectroscopic properties with the salt of natural Cephalosporin C. It remains to express my very warm appreciation of the privilege of having been associated in the work which I have described with an outstanding group of colleagues at the Woodward Research Institute in Basel, Doctors Karl Hessler, Jacques Costelli, Peter Nage, Wolfgang Opholzer, Robert Ramage, Subramania Ranganathan, and Helmut Vorbruggen are those whose high experimental skill and unflagging spirit brought this investigation to its successful conclusion, and I am glad to have this opportunity to express my admiration for their achievement. Okay, so everyone, that was a dramatic reading. However, that was done intentionally to make sure that I didn't lose anyone due to the longevity or the duration of the text. And we're also trying to implement more engaging content that combines science and art. And the artistic side of that is the dramatic reading. The science part of it is the text itself. Now, analysis of these speeches will come later. However, we are releasing the speeches. Of course, these are publicly available on nobelprize.org, Nobel Prize Outreach, nobelprize.org, and so let's reflect on the key takeaways. So I hope I didn't lose you in the discussion of the text. The goal was to communicate what he said first and foremost, and then analyze it afterward. But before we get to the analysis, some key takeaways that you can take away from this episode. What is cephalosporin? Cephalosporin C, as discussed in Woodward's speech, is a product of the metabolism of Cephalosporin acromonium, which is a type of fungi. What is penicillin G, otherwise known as benpen? According to PubChem, a broad-spectrum beta-lactam. So it's a type of penicillin. It interrupts bacterial cell wall synthesis and results in the weakening of the bacterial cell wall and eventually causing cell lysis. Now, why should we care about this? Now, this cephalosporin synthesis, the total synthesis of cephalosporin C, it was so pivotal. It helped advance the field of natural products and drug synthesis. Woodward did a lot of good work. We could talk about the Woodward-Hoffman rules. One of the things I did my undergrad thesis on was Woodward's collaboration with Albert Einstein Moser to map out the synthesis of vitamin B12. Woodward did a lot of significant work in the field of organic chemistry and other areas as well. So it's worthwhile to read his speech, make sure that it's understood, and then analyze it afterwards. So once again, you have it. This is the New Chemist podcast. We're glad you're listening. Feel free to download this podcast on TuneIn Radio, Anchor, Odyssey, and Apple Podcasts, and other platforms. On this podcast, we discuss chemistry, which simply put is the science of change. Also, we discuss careers, research, and Nobel Prize laureate speeches. We also interview thought leaders, science professors, educators, administrators, and pioneers in their respective fields. So thanks again for listening. So glad to have so many listeners out there. Today we discuss Woodward's work. Please note that ideas and perspectives reflect those of my guests, and the guest today was someone from the past, Dr. Woodward. My guests and I. Thanks again for listening. Thanks for listening. We're glad you were able to tune into this podcast. Once again, this is The New Chemist, where we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Thanks again for listening. Note, the views on this podcast represent those of my guests and I.